But we can give it to Freddy first, okay, and then give it to Per. Per is the rector of the research.
Yeah, this is for live streaming. And
Yeah, but I think we just put it here.
It
What
was
does what?
It was an echo.
But that means I have to give all them this one.
You will do that.
Ah.
Put on a post somewhere.
Okay.
You can either use this one or this one.
So why is that not making echo? Why is that not making echo?
No, when it is far from you.
Yeah, and then there is a time. Okay. Okay. Super.
But I'm already in this core project.
Yes, good morning, everybody, and welcome to this inauguration of X-Power. My name is Frede Blåbjerg, and on the program here you can see I was not necessarily the inventor, but at least the start-up of this initiative we are going to celebrate today. A special welcome to Per and Thomas and Ryan and Hanne to take the time here and also speak in that respect. But also a special welcome to all coming from outside. They are also internal, but taking the time to come up here. Well, maybe in 2 weeks, this was not possible. Let's see. We should not be dark people, but we never know what's going to happen. But now we realize it. Well, this place here is X-Power Aalborg. By that I mean it's an infrastructure which is which is covering the whole country in Sønderborg, in Odense, in Hørsholm, in Lyngby, and then of course also 2 locations here in Aalborg, the materials department and also the energy department where you are here today. So I would say in that sense it's also an interesting initiative. So of course X-Power, I hope you know a little about it, but it's about prediction. And prediction, this is very difficult, especially about the future. This is what we are trying to do here by this facility, because what we intend to do is to try to say something about how long time will products, electrical products, be able to operate in the future when they see certain loading conditions. And well, you can say, haven't we done that for a long time? Yes, we have, but we are becoming better and better to understand and describe how components, how materials, how systems are operating, wearing out, in order to say something about what is the probability that a product series will only have, let's say, 0.1% failure after 30 years of operation. So this is what we intend to work with, and in that respect we need to test, we need to analyze, and we also have to use this information to improve the things we are doing. Well, we started with this initiative, I would say, already 2010-11, where we started up Center of Reliable Power Electronics. Then I would say we have had a lot of different projects with companies here since then. But then around 2015, there came an opportunity for us to volunteer ourselves to come on a Danish roadmap of research infrastructure. And this research infrastructure is managed by the Danish Education and Ministry, Education and Research Ministry. We came on the list of, let's say, I think it was around 30 different proposals. And I would say then 1 year passed, 2 years passed, and we did not get money. So we became a little bit uncertain if that could happen. But then suddenly it happens from one day to another, thanks to people who have been working in order to promote this activity. We were able to get around 32 million Danish kroner to establish this research facility between the different partners. And then the universities was asked to do some of the same funding. So that means in total we have invested in research infrastructure for a little bit more than 60 million in respect to that. So this is a good investment, I would say, a significant investment we should appreciate. And let me also here say thank you to our partners, but also Aalborg University that you gave us this opportunity. And also maybe here at Aalborg, I would say thanks for the patience, because when we were going to establish it, we had last year and we had this year. What happened then? We had very good plans. We got Corona. And how do you build infrastructure if the research, if the university is locked down? Well, we cannot base this on simulation, unfortunately. So it has to be built up. So that means also we have to say that we have a lot of fantastic infrastructure operating. We also have a small weak spots in some of the infrastructure we still need to finalize, but we wanted to make it inaugurated now and so on. So thanks for that. So in order to make the day to be a good day, we have fundamentally 4 parts. One part is this opening. A second part is a presentation about the facilities. Then a panel discussion from industry. Part of our stakeholders, we should remember, this is not only for industry. This is also for research and take the next step in terms of predicting about the future. So, but we will have a panel discussion about what can it be applied for, and then there will be site visits for you people who have signed up for that. At the end, before I give the floor to Per, I would say very, very special thanks here to Francesco. I gave you, let's say, the opportunity. And you took the challenge and leading this in a very good way. You had the experience. Also to Amir, you have also been working very hard, and why also working very hard, and then also many others. We come a little bit back to that, but they have been you have been the key players for making this happen, together, of course, with our partners from outside. So also thank you to Sabrina and Bonnie. They are not here, but they kept track of the money, and that is good to have some people who help us to ensure that we are on the right pace. So with that, welcome again to this inauguration, and I will give the floor to Per. I think you should have this one on, something with the live stream.
So now we're ready for live streaming. Thank you for that. And thank you for giving me the opportunity to welcome you all here today. This is indeed a great day for Aalborg University. The official inauguration of the Danish Power Electronics Reliability Test Center, or in short, X-Power, marks an important milestone. I'm proud to be the rector of a university with researchers and research environments that not, quote, only, unquote, host world-leading researchers, but also can make a potential world-changing investment here. We owe to you, Professor Frede Blåbjerg, and your research team, all of you, together with our colleagues and partners at University of Southern Denmark and the Danish Technical University and Force Technology, a special thank you. Thank you for your work. Thank you for making a difference, not only in science, for the way we view and understand the mysteries and utilize the potentials of power electronics, but also for the difference your effort make in solving some of the world's great challenges. Power electronic is indeed a key technology in the green transition. With the transition to renewable energy as an energy source, an increased focus on energy efficiency and the electrification of the transport sector, the need for power electronics solution has indeed increased explosively. Power electronics is what binds the technologies together, and with X-Power we tie a knot. It's a unique collaboration between University of Southern Denmark, the Technical University and Force Technology, as well as Energy and Mechanical Engineering at Aalborg University. It has no doubt been a very difficult process. As Frede also explained to us, in times of Corona, this has been quite an ordeal. And in establishing a center and partnership of this magnitude in the middle of a pandemic has certainly not been a walk in the park. But now we have reached the point where we can offer tests for researchers and for industry. Create the foundation, create the space for researchers from different knowledge institutions to test their ideas, a place where companies can get their products tested as well. This is the pivotal point. If we are to tackle complex scientific phenomena such as, for example, climate change, with any hope of helping society, then we must put even greater emphasis on cooperation between political institutions, businesses, and academic expertise. This is our main mission. For more than 10 years, Aalborg University, in conjunction with Danish industry, has been working to better understand the reliability of power electronic systems and incorporate this knowledge into the industry's design. Understanding how long power electronics last is vital for optimizing the individual apparatus and for creating a secure electrical system. X-Power is thus a fundamental test of infrastructure that will model and test the reliability of components. It is crucial to be able to validate the models we use so we get things right. A fault in an instrument may be fatal, not only for the product, of course, but also for a company. I would also like to take the opportunity to thank you, representatives from industry, for your contribution and your commitment to constant collaboration. Thank you. I'm delighted that Aalborg University is leading an infrastructure project supported by the National Committee for Research Infrastructure that so clearly supports Aalborg University's strategy to help address a number of the SDGs, creating knowledge for the world and facilitating world-class research for a large group of researchers of the country's universities. As rector, I look forward to the results that will inevitably derive from such excellent infrastructure. Thank you, and once again, a heartily welcome.
Thank you very much, Per. It will be hard work.
And now you are ready as well.
The next presenter will be Thomas, not Bull, but Ebel. Thomas Bull could unfortunately not make it today because of some private issues. But Thomas, he is a super stand-in for that. So welcome, Thomas.
Thanks a lot, Frede. Dear ladies and gentlemen, dear Frede and dear Per, I also would like to welcome everyone on behalf of the South Danish University SDU to this ceremony. My name is Thomas Ebel and I'm heading Electrical Engineering of SDU, including the Center for Industrial Electronics in Sønderborg. I'm standing here right now to substitute my head of department. Frede already mentioned Thomas Buhl, who could unfortunately not be here, but he is sending his best regards and wishes to this inauguration ceremony. Understanding reliability of power electronics is key to support, as it also was said, the future megatrends like digitalization, renewable energy production and distribution, as well the electrification of the transport sector and others. We are right now in a phase where new materials, like for example the wide bandgap semiconductor devices, are introduced into the market. And these new active components are also new passive components to set up a functional power electronic device. And in this field, SDU Electrical Engineering and the Center for Industrial Electronics have strong competences, especially in the understanding of magnetics, capacitors, and their integration in ultra-compact industrial applications, power electronic applications. These material scientific aspects of power electronics are very important. And therefore, we are very happy to be involved in this Danish infrastructure project, X-Power. We believe that we can help many companies in Denmark and abroad improving their reliability and the performance of their power electronic designs and devices using our know-how and equipment. And later in my talk in a few hours, I will go more deeply into that. I also would like to use this occasion to thank especially Frede and Aalborg University that SDU could be part of this Danish infrastructure and very important project. And also thank you for being here today in Aalborg to inaugurate with us this inspiring project, and I wish us all a very interesting and inspiring day. Thank you.
Okay, next speaker is Ryan Ambach from DTU, and luckily we also got him in the project. So.
Thank you, Frede, and ladies and gentlemen and Pierre, good morning. And so I'm here on behalf of the Center for Electronic Corrosion at DTU. And first of all, I would like to extend my warm welcome to all of you to this inaugurating function of X-Power. And we are very proud to be part of this project and is establishing the unique and broad level infrastructure on power electronics. And thank you, Frede, involving us in this project and together with SDU and Force Technology. Like any other university, the strategic vision of DTU today is the sustainable future by developing value-added technology for people. And DTU develops value-added technology, exploiting the synergies between research, education, and innovation with a commitment to sustainable development. And also, we focus on educating the engineers and researchers for these aspects, also to change the society and also to help the industrial development. And that means that today the sustainability is a formal and active learning objective in all our educational programs. And as all of you are aware, the three corners of this research education strategy, and today, like any other university as well, is the digitalization, circular economy, and green energy transition. So all of us knows that the reliable power electronics is a key component in the digitalization and green transition. And the vehicle electrification is taking at a mega rate today, and the reliable power electronics is key for this development. And so therefore, establishing such an edge power infrastructure facilities covering all over Denmark is not only timely, but also the need of the today and strategic. And Cellcore D2 is contributing this objective within the climatic reliability of electronics area, and we are leading in this area over the last decade by helping the industries. Widespread use of electronics for demanding applications today is actually challenged by the use of the electronics in different climate, and that influence and causing many failures. And as we increase the power and voltage in the power electronic systems, and also when we use that for the electrification, and the automotive has to work in all kinds of environmental conditions, and this is going to be much more challenging in the future. And so addition of several test facilities as part of the S-Power infrastructure at the Cellcore DTU with the existing test facility and expertise can play a big role in tackling this issue, not only for Denmark, but also as we have done over the last decade, and not only in Europe, but also globally. And so once again, I welcome you all to this function and looking forward for more collaboration with all of you in the future. Thank you.
Thank you very much, Ryan. And next speaker is Christensen from Force Technology, and we have had a long collaboration with them. And you take that one. Is that better?
Is it function?
I think so. Maybe we need an expert.
Jeg prøver at sige noget.
Ja, det er perfekt.
Ja, det er fint.
Super. Så tak.
Tak.
Yeah, please.
Good with experts, I can see. Thank you. Thank you for the invitation to come here today and give a speech on this opening of this X-Power. And first of all, I would say congratulations. Congratulations with this new important network of test facilities that can help raising the level of power electronics in Denmark. As director for a GTS institute that has a close and daily collaboration both with Danish companies and also with the universities, and as by myself a strong advocate for Denmark as a leading test nation, I think that PowerX is a really good news, as we also have heard from former speakers. It is incredibly positive that the universities are supporting development of the best facilities in the world. At Force Technology, we are collaborating every year with thousands of firms, and they use our test facilities in high demand because they provide access to special knowledge, equipment that the individual companies do not possess by themselves. In the same way, X-Power will advocate for knowledge and technological development. X-Power will be able to do things that go far beyond what we can today. And it's going to be a place you go when you break new grounds and need help to push the boundaries further. Combined with the facilities we have in the GTS institutes, networks like X-Power can make Denmark as a unique test nation. A test nation in which GTS's universities work together and transforming new knowledge into solutions that meet the standards and the needs of the market. We are in a small country, but we want to compete and take the lead globally, and we have to work together and use resources wisely, exactly as X-Power intends to do. Speaking of resources, the most positive things about X-Power's facilities is perhaps that they give us the opportunity to make power electronics and electricity conversion more sustainable. The focus on using resources wisely have never been greater, and the best energy is the energy when we do not use. With a strong network of test facilities that strengthen research in power electronics in Denmark, hopefully we can become better at reducing energy energy loss and when transforming electricity. And hopefully we will also make the product to live longer. Whatever it is, a pump, wind turbine, or something else. It is not only important element of the green transition, but it's fundamental part of the sustainability. I especially mention pumps and wind turbines because some of our largest important Danish companies such as Grundfos and Vestas are driving a green transition forward. Everything they do, right down to the individual component, has to be sustainable, and it's important to them that no resources are wasted. Therefore, they will benefit greatly from a network of test facilities like X-Power. And of course, we also have all the SMEs in Denmark, which are such an important part of the Danish business community and the economy. Sometimes they stand in the shadow of the big firms, even though they are at least important for the Danish society. With a strong innovation system and a state-of-the-art testing facilities like X-Power, we can strengthen SMEs and thereby strengthen Denmark. I'm sure that X-Power will have a significant impact on research here, both in Aalborg, in STU and in DTU, on companies and on Denmark in general. It will be very exciting to follow X-Power. Thank you.
You are very skilled. Okay, you are very skilled in using this one. Thank you very much. So now we go a little bit to what we call the official opening, and let me just instruct shortly on that. Due to Corona, we cannot be on 10 square meters altogether. Not because we are, let's say, small facilities, but the idea is that the four speakers here, they are going to the facilities, and there we have the possibility to mark the opening of this. And what we will do is that you stay here, the rest of you, and then you can see live stream what's going on there. I'm sorry, but if now because of Corona and so on, let's do it in that way. But what you then have an advantage is that outside reception where you can get a little bit, not champagne, but in the same style. We are not allowed champagne here. But and you can enjoy, and then I'll show you around in the facilities. So this is the next step, and reception, and then afterwards we start up and do a presentation about the different facilities we have at the different locations. So just stay calm, and we will go to another place.
Freddy, you can use it with yourself if you want.
Yeah, so over there?
Yeah.
Okay. Yeah, so we have to go outside a little bit.
Let's sit down. Francesco.
Yes, I think you can. Can you hear me? Yes. Yeah, okay. You can accept.
Okay. So I hope you enjoyed the reception. So now we go to the second part of the inauguration, and this is a technical presentation by the partners in the X-Power. And the first presenter is AAU Energy, and Francesco Iannuso will present the facilities and services offered by Aalborg University Energy Technology, before and energy now. Yes.
Thank you, Amir. Can you hear me? Yes. So again, thank you and welcome. I'll be introducing very quickly and hopefully efficiently our facilities here, sitting at this very place, so at Aalborg University. Yes, my name is Francesco Iannuso, and I'm proudly part of X-Power collaboration. I'm professor here in this department from 7 years now, something like this. So I think everyone in this room is aware about what the challenges are in terms of power electronics industry in respect with reliability. So we want to be able to make robustness tests, testing to the limit, understanding failure mechanisms, predict a lifetime based on mission profile, not just average lifetime, root cause analysis, what went wrong, and how can we improve it, condition monitoring, getting aware of what the status of damage is, multi-stressor reliability assessment, what happens when you have one stressor, when you have the other stressor, or when you have both applied together. And of course, CAD tools, software tools for reliability prediction, or I would say lifetime estimation. As some of the personalities have been mentioning in the beginning of the day, we have a big challenge in front of us, which is called the green transition. And we feel like reliability is a big part of the story, because we have to move to 100% we have to move to 100% renewable in a relatively short time, in basically 3 decades or something like this. And this is true for most of the European countries. We have to bear in mind that power electronics is an enabling technology for renewables, because you have to turn an energy form which is not constant, think of solar radiance or wind speed, to something which is more constant, for example, frequency-wise or voltage-wise or something like this. So power electronics is very essential to make this happen. And of course, its reliability is affecting the overall energy conversion reliability process. And we have to bear in mind that basically this is absolutely clear as of the time being, that I would say the largest part of the failure overall come from the power electronic system. So we have a big challenge in front of us, which someone can also call opportunity, which means making power electronics more and more reliable and make this transition happen in the smoothest possible way. This is what inspired X-Power over a long time now, and this is what we are struggling with. So what kind of services, very concretely, we can offer to industries, and not only industry, also research institutions, not just from Denmark, but also rest of Europe. I have a list here, non-exhaustive, because I don't have much time to do this. But anyway, we got inspired by this picture. By the way, credits to Huaiwan, my colleague, who was basically the visionary behind this. So the idea is we want to move from test sample preparation through reliability testing implementation at 2 different levels, system level and component level, ending up in post-testing analysis. And then, of course, giving some feedback in order to, to learn from failures, from mistakes, and design even better components. So this is the paradigm we have in our mind from the beginning of X-Power, and this is the kind of the question we are trying to answer with the X-Power collaboration. All right, so I will go through this I would say, paradigm very quickly, starting from testing sample preparation here. So in this case, we can offer a 3D printing service, which I would say relatively reasonable dimension. I would like to mention this because you may consider sample preparation like something which has to do necessarily with electronics, which is not the case. You may need to customize your sample platform, your test bed. You may need to design your heatsink in order to be able to forge some given thermal profile, temperature profile, or even a mixed, thermal, electrical, thermal, humidity, vibration, and something like this. Designing a metal heatsink is now possible, such this ones here, given the capacity we have, also for aluminum, stainless steel, and copper and titanium, which are actually close to become real, but not only. Testing implementation, we have a large set of things we can offer here, starting from the system level. So we have this halt vibration chamber, which is capable of 6 degrees of freedom between 5 and 70 G RMS, together with the high and low temperature range. And the objective here is to make tests to the limit, to work out what the I would say the weakest link is in power electronic systems. We have thermal imaging, which is a big part of reliability studies, because basically reliability is heavily related to formation of hotspots when it comes not just to semiconductors but also to system levels, to system level reliability. So we decided to improve our equipment with very fast on the one side and very high resolution on the other infrared cameras, which allow us to look at systems into operation and work out what the weakest points are. Another example of what we do, oh, by the way, all these things will be possible to be seen during the afternoon's lab tour. So basically, this is just to give you a rough information, but then you are welcome to ask questions during the tour. Another significant example, it is shown here in this picture, where we both show a couple of exemplary chambers. This one is what we call the explosion-proof chamber, which is very suitable for, I would say, risky operations like short circuit and something like this, as well as the testing of batteries, for example, which can catch fire or even trigger explosions. But also this one is very nice. We call it elevator chamber. And the reason why it is done like this, because it embeds a heat pump which is able to cool down the bottom part and heat up the top part, and you can shift the sample up and down in order to provoke a very, very steep temperature gradients during your mission profile. And we have a bunch of other I would say rather normal chambers, ovens, and similar things. We are all going to visit during the afternoon session. More on the, I would say, mission profile side, we have a set of systems. This one is the one looking at the PV systems. You may know that in PV systems, basically, you have at least 2 ports inverters. One is with the panel array side. The other one is with the, I'm too far from the receiver. And the other one is from the grid. You may more and more frequently, you may have a 3rd port, which is the battery port, basically. And what we can do here is to simulate all the rest of the environment, but the converter itself. So we can offer here, what we can offer here is to test the company inverter, for inverter manufacturers, of course, under very specific mission profiles. For example, what happens if you have a grid sag or whatever it is when the solar radiance is maximum, right? So you can simulate such kind of conditions. And you can also monitor what happens at semiconductor level with some optical fibers or another kind of sensors as far as we have access to the semiconductors. Another example I have is related, very similar, actually it's related to testing for motor drives. The concept is the same. So what we want to do here is to simulate all the rest. So we simulate the machine, the rotating machine. So we have a more powerful inverter, which is simulating the load, the torque, the speed, and what happens on the mechanical side. We have the grid simulator on the other side, and the inverter is tested in between.
Again, we can subject the inverter to a given very customized emission profile, and we can monitor what happens at the semiconductor level temperature-wise. Another facility we have been investing a lot on is what is called high-power linear amplifier. The point here is that nothing is ideal in nature, in reality, and neither for I would say equations and something like this, but also for the grid. So the grid is not ideal. You have to be able to simulate what real grids look like from, I would say, from an electrical point of view. So we are able to simulate for a large amount of power. You can see some numbers here. We are able to simulate what happens in case of distorted voltage and currents, and we can, of course, play with the harmonics. We can inject harmonics both on the voltage and current side and test, specific apparatuses which are supposed to be grid connected and to react in a given way. Calorimetric loss measurement, which is also something which is, I would say, rather original of our facilities, is becoming more important when it comes to accurately working out the converter losses. The reason here is that normally what we do is by differential measurement. We measure output power, input power, and by this difference we work out what the losses have been. This is possible, you can do this, but when you have cooling systems, then you have to subtract, of course, also the losses going to the cooling system, and then you work out what the hidden losses are. You can do this, but when you are dealing with very efficient systems, the amount of losses may be very negligible. So this means that you need a calorimetric measurement system, and we developed it. So what we did, and it is possible also to visit later today, what we did is to build up a fully customized facility. You can see a cross-section here where we circulate air and measure airflow and air temperature difference to work out what the losses are. You can see some numbers here regarding accuracy and regarding flow speed and something like this. All right, what about component level? Remember the other part of the reliability testing implementation. We have a thermal impedance characterization. We have actually two machines we are going to show as well, able to work out what the thermal impedance is of a given setup, of a given power stack, thermal stack I should better say, which is very key, very important to work out what the expected junction temperature swing is going to be. This is a relatively, I would say, high power facility. We are able to work tests up to 1800 amperes, I think 12 volts or something like this, and work out what the thermal response is. That's not enough. We have something which is even more. We can reach up to 2400 amperes, 4 channels, 600 amperes each, with basically the same goal. So we are able also to operate tests in parallel, not just because we have two machines, but also because each machine has independent channels we can operate independent of each other. Capacitor characterization, which has become a very, very hot topic. What happens when in power electronics applications you have a back-to-back converter with a common DC link in the middle. You have a capacitor, normally it's a capacitor bank, which is subjected to current ripple at a given voltage, and this current ripple, of course, is wearing out your capacitor. So can you simulate what happens in real life? The answer is yes. We try to answer this, and what we did is to design, to custom design a facility where we give voltage and then we inject a current ripple to a given frequency and shape and amplitude, and we work out what the capacitor life is. And this happens in parallel to temperature, temperature and humidity, because it works together with a climatic chamber and, of course, a degradation monitoring system. Laser refractometry, this is an innovative technique we are setting up in these months, basically at Tilburg University, which is able to work out what the temperature evolution is during very fast transients. So you can imagine a short circuit, but not only, where you want to work out what the temperature rise is during tens of microseconds and something like this. There is no equipment at the moment able to do this. We believe we found a way to work this out. Power cycling, which has become very actual. One of the outcomes of the first work done at Tilburg University was that AC power cycling may lead to different results in terms of number of cycles to failure than DC power cycling. This is something we took as a mission. So we decided to develop and introduce a facility which is able to AC power cycle components. So what we do here is to subject our components to AC, as in real life, basically, and work out what the expected life is. We have a set of 6 channels here. This is a picture of one, and this is also something we are going to show you in the rest of the day. Very quickly about post-test analysis. Here we have a decapsulation service, which is basically a machine which is able to remove either molded modules resin, the black one, which is typically used for discrete components like this one in the background picture, or remove gel, which is very selectively, which is very useful for inspection, for working out what the damage of the single chip has been without affecting the rest of the module, without treating, without removing the entire gel from the module. Magnetic component characterization, which is something which is also very important when it comes to power converters, because magnetics can also degrade. I'm talking about, of course, windings, which is number one degradation mechanism, which is about isolation paint, but also magnetics themselves. If subjected to over temperature and something like this, they can degrade. So we are able to characterize them before and after test. And one of the last things I would like to introduce is semiconductor characterization, both from a static point of view. Many of you know this kind of equipment, which we have in-house, which have acquired in-house up to 10 kilovolts and 1500 amperes capacity, but also this other equipment, which is a little bit more rare, still from Keysight, where we are able to execute double pulse testing with very, very low inductance levels, which is typically needed for testing gallium nitride components. That's what I have. I have to apologize for being a little bit long in time. Thank you very much for your attention.
Thank you, Francesco. I think all the services that you have seen here was not possible to be realized without the help of the X-Power team. So let me invite the X-Power team come here to give applause to them, at least for AU Energy, because we have also some other people in our department. So please come here, and I ask everybody in the audience to give applause to them.
Can you take a photo?
Yes, it's a big team.
A little bit higher.
Everybody. So the next presenter is Christensen, who will present the facilities at AAU MP Materials and Production Department. Yes.
No, I should be doing this one then. Yeah. Just wondering why nothing comes up. One more screen. Oh. The other way around. Try something else then. Sorry, is this one on? Yes, it is. I can hear. Okay, hello, my name is Christensen. I'm from Department of Materials and Production. And of course, materials is a very important part of power electronics. It's materials that break. Our part of this is very much to look at failure analysis of the structures, post-failure analysis, stripping them apart, digging in to see what actually went wrong. And this could be part of looking at components that have been in real-life use, or it could be part of a test program that is set up. So we run accelerated tests on structures and take them out at different times and then look at them. We also do fabrication of prototypes of small elements. We don't make complete power chips, but we could look at contacts in power electronics. We could look at packaging problems, packaging issues, development of new materials, and so on. Our power electronics part is placed into the NanoLab, the clean room facility, and the clean room is based on wafer production. So we do lithography, we do etching to put the structures into the wafers. We can add something with adding thin films, and always characterize what we do. And it's kind of a circle. Whenever you build components, you go through this a lot of times to build up a structure. Now we put X power into this, so it's put in together with all of these things that we already have. I forgot to mention that it actually is placed 1,500 meters. It sounds to me somehow less than 1.5 kilometers. But anyway, it's somewhat remote from this. The main part of our department is just next door, just over here. And eventually this thing is going to move down here. But you know, with public constructions, it's not something that goes fast. It takes time. But it's eventually going to be like that. So I'm going to dig into some of the things that we have built up in X-Power. The first thing you want to do if you want to look at failure analysis is to take the component apart. So try in a well-controlled way to dig into where the problems might be. And we have done that over time. This is an example of a wire bond. This is the heel where you see crack starts to develop. It's amplified a little bit up here. And we've been doing that over the years, trying to find our way into where these cracks are and how they develop over time, try to model it and so on. This is now becoming somewhat easier because we have a professional system for it now. It consists of 2 units from Leica. The first one where you can cut in with a diamond saw under a microscope and try to isolate the part that you want to look at. Afterwards, in the same machine, you can polish mechanically until you have a smooth surface. But this leaves you with something that's damaged, with strains and so on. So you can move to an ion beam system, which has 3 ion beams. You can see these blue dots there that hits the sample, and so you can spot away with ions to have a stress-free surface that you can analyze afterwards. Everything is under an optical microscope, so you have a nice control of what you're doing. You can cut at low temperature, under liquid nitrogen temperature, which means that you can take polymers, soft materials also, and cut into them. So everything can be under controlled circumstances. The first thing you want to do when you have cut into it is to look at it with a microscope. And this is a microscope image taken with an optical microscope with cross polarizations. This enhances the grain boundaries that you could see, or the grains, so you can see contrast between different grains. We have a number of different microscopes. If you want a higher resolution, you go to an electron microscope. We have 2 of those in the clean room. This one has also an ion beam sitting here, so you can actually cut into something. Here's an example. You cut through the metallization of a diode. and you can go in and analyze the cross-section. And afterwards, you can do a chemical analysis, spatially resolved with the electron beam, because it generates X-rays that come up to an X-ray detector that sits there. This here is an example of using electrons scattered backwards in the microscope. We've been looking at the diode of an IGBT and realized that just thermal cycling of the diode created a very rough surface over time. So as we kept on cycling it, the surface got more and more rough. And we then started to look at that. This is an image of the grains that you can see. Then we focused down to one grain. We have made some marks, which means that we could take the sample out. We can do a new cyclings, go back and look at the same grain, try to find it because we have made some marks on it. And eventually you can see that the grain splits up in more and more grains. And this is what gives you this very rough surface that eventually makes the bonds that are made to this break. So these are the opportunities you get when you start to look at it with electrons. There are other possibilities with microscopy. You could try to look at it with scanning probe microscopy. And AFM is the most well-known to you. Probably you take a sharp tip, you scan it over the surface, raster scan it, and you take the height variation as a kind of an image of the surface. This is maybe the simplest way. There are other contrast mechanisms that, because as soon as you have, for instance, something that's electrically conducting, you can start to look at the potentials that are there. So Kelvin force probe microscopy is one of the specialities that we have. You can do it on different atmospheres, sample sizes. You can see the height resolution is a fraction of a nanometer in a system like that. This is an example of looking at gallium nitride, aluminum gallium nitride wafer for high electron mobility transistor. And how thin can the barrier layer here be on the top? So it's varied here, the barrier layer from 1.5 nanometers up to 12 nanometers, and you can see from the electrical potential that it gets more and more homogeneous. So making the layer too thin simply doesn't work. You can test properties in addition to just the geometry of systems. You can start to look at also electrical properties with the microscope. Then there's a chemical analysis. This headshot thing with things coming out all directions is originally a secondary ion mass spectroscopy system where you can do depth profiling. So you send in ions. These ions knock out the ions of the material, and then you just put them into a mass spectrometer. So you take their weight, and then you know what you have. And then you just sputter through the sample. This is an example of a high-temperature reflector, aluminum oxide on the top, then some tungsten layer, aluminum oxide, tungsten again. And you can see the first tungsten layer, the second tungsten layer, and then you anneal it in 600 degrees at free air, and you can see that suddenly you don't have the sharp contrast in the system as you had from the beginning. So clearly not too good a reflector. You could also look with X-ray photoelectron spectroscopy. So you send in X-ray from the source here, and you look at the electrons that are coming out to the spectrometer and analyze the energy. And you can see this is just a simple example of a polymer put onto silicon. You have some carbon, you have some oxygen, but you can also resolve very sharp details in these spectra, and this tells you something about the chemical bonding, so we can go back and figure out how are actually the atoms bonding to each other in this way. Everything is with a load lock, and you can put things in. You have two ion sources, so you can use both organic and inorganic materials in the system. Then we have an extremely nice cluster thin film deposition system here. It consists of two chambers, one for electron beam and one for sputtering. Nobody here knows if I was pointing at the right ones. I don't either remember which is which. They have a nice base pressure, 10 to the minus 9 millibar, and you can actually take the sample up to 1,000 degrees in them. These are quite unique things for a deposition system like this. They are coupled with a robot in the middle, so we're actually looking at the back side of it. From the front side, you just see.
So you can just visit the website and you can contact Kelvin. So the next presenter is Thomas to present facilities at the University of Calgary, Denmark.
Can you hear me? Yeah. Takes always a few seconds to. Yes. Mm-hmm. Have to go to the right slide and then we can start. Do you have a laser pointer? This one?
I forgot. Do you want this?
No,
one
no, I
also?
don't need that. I need only the laser pointer.
Yeah,
This
it's
is-
just a
Yes. Yes, welcome everyone also from my side again. So I will present two X-Power labs at SDU. So one at the Center for Industrial Electronics in Sønderborg and one in the Tech Campus in Odense. And as I said already, we are specialized mainly in the investigation of failures of passive components, so capacitors and magnetics. So this is a chemical lab at the CIE in Sønderborg. We have dedicated this chemical lab mainly to the X-Power project, and we have here, I will go through the equipment later, but before that I want to make you understand why this needs some backup. I don't know why everything. Yes. So why chemical analysis is so important for understanding power electronics reliability? This is, for example, an ESR, a development of a capacitor over the lifetime at a certain load, and you see that some components very often show an increased ESR value. And you can, of course, deterate capacitors, you can deterate a lot of capacitors, and you always observe that, but you don't understand why. And we are looking into that, what is happening, what is ongoing in an electrolytic capacitor. And the ESR is strongly dependent on an electrolyte in an electrolytic capacitor. And when you investigate a fresh electrolyte, it looks like that. There's maybe one component inside the electrolyte which is, let's say, responsible for the device. When we speak about reliability, also very often contact issues are a root cause for failures. Therefore, we have to look into terminals. So we have invested in an XRF system, which allows us to investigate solders and solder metal compositions. So if you, for example, have a solder which is de-riching of tin or getting certain defects engaged, we can measure this with this tabletop instrument. Further, we have also already existing electron microscopes and also a so-called helium ion microscope, which is available at SDU, and therefore we have invested in tools which allows us to mill down certain cross sections of components to put them in a microscope. Another topic I would like to discuss are polymer investigations, and based on polymer metallized film capacitors. They are one of the driving components in windmills, for example, and they're also exposed to certain deterioration reactions. And we have now invested in a gravimetric analysis method called TGAs. In fact, it's a kind of balance where you could expose, for example, polymer to temperatures, and then you see how, in dependence of the temperature, a certain polymer is deteriorating, and we can measure the weight loss with this system. And now we can attach this also to our mass spectrometer. So we get also defined mass loss informations during load operation in metallized film capacitors. Yes, another thing which is quite important are breakdown testings, because we are exposing power electronics to higher and higher voltage levels, and that means that insulation materials must withstand also higher external voltages. And we have to understand how those insulation materials are behaving under such high field conditions. And therefore, we have the chance to use a so-called partial discharge tester. That means we can see how many coulombs, for example, are bypassing a dielectric under such conditions, and we can also expose such polymers before thermal deterioration reactions and can see how partial discharge is influenced under these load conditions. Second, we are working with breakdown testing. We have high voltage breakdown testers in our lab, because it's also crucial to understand new capacitor developments, which we are also, by the way, doing and performing, and how we can assess then breakdowns of such new polymers under certain field conditions. Then I'm coming to our lab in Odense. Here, Morten Newman is responsible for that lab. Unfortunately, could not be here today because he is ill. But nevertheless, I would like to present his facilities. So in Odense, he is mainly interested in the understanding of new modern DC-DC converters, and especially the magnetics in such systems. And he is working on planar transformers, and therefore he has seen that there's a need to investigate, for example, with a pH analyzer, with the hysteresis analyzer, the properties of magnetic materials in such systems. And therefore we have now two labs in Odense dedicated to this work. So one is a laboratory dedicated to system analysis and thermal measurements, and a laboratory dedicated to magnetics and parasitic component extraction. This is the other lab. As I said, he is looking into magnetic materials with an Iwatsu pH analyzer and the infrastructure around that. I think this device is also available here at Aalborg, but due to his work in the study of magnetics, this is also relevant very much relevant for his work under his, let's say, aspects. And so he is capable to investigate new core materials, new ferrites, and to measure, let's say, the classical hysteresis behavior of such materials. Then also he is invested in an impedance, high accuracy impedance analyzer from Keysight, and he can measure here impedances from 25 to 40, from 25 milliohm to 40 megaohm. And he can also use this built-in equivalent circuit models to in these measurements. Also, when you build up DC-DC converters, also the semiconductors are relevant, especially GaN is in focus here in our lab in Odense. And so we have here invested in a curve tracer where we can measure the switching behavior of such gallium nitride, mainly MOSFETs. And he is a relevant, let's say, equipment to characterize such semiconductors in his lab. And to expose them to low and high temperatures, we also have a thermo stream there, which is also available in Sonderbox. We have two setups, so one in Sonderbox and one in Odense, but this Sonderbox setup does not belong to X-Power, so I present this setup here. And here we can expose the switching devices to temperatures from -80 to 225 degrees Celsius and investigate their switching behavior under these conditions. Yes, and then the second lab about system analysis. Also, let's say, have a thermal camera available, maybe not as.
What we do at the Center for Electronic Corrosion, and also in between I'll tell a little bit about how the SPR facilities are helping us. And towards the end, I will show a video and that profiling the labs and the equipments. So at the Center for Electronic Corrosion, we focus on climate reliability of electronics. This is working, or I'm not sure. Yeah, so we focus on the climate reliability of electronics. That's our focus. And so all the EXPO related facilities, what we established is to reinforce our test facilities and expertise in this area. And the Center for Electronic Corrosion is established in around 13 years back, or 14 years back in 2007, because of the interest of many of the Danish companies, like Danfoss, Grundfos, Vestas, and other companies. And everything what we do at the center is to understand how the climate is influencing the electronics and how that is causing the failure, and understand the mechanisms and also this intrinsic and extrinsic way of improving the climatic robustness. That's what our focus. I'll come to that a little bit on what is this extrinsic way of improving the robustness means. We work in close collaboration with many companies, not only in Denmark, but also all over Europe as a part of this activity. I think all of you are aware of why this climate reliability of electronics is important today, because electronics is used everywhere. So that means that it is getting exposed to harsh climatic conditions, and that causes several electrochemical or corrosion type of failures. And these failure modes are increasing because, not only because they're exposed to many different climatic conditions that cause exposed to humidity and temperature, and also it can be the corrosive gases, and also there can be other residues also coming from the atmosphere. And there are many internal factors also related to the electronics that is causing this failure. And if you look at today, the miniaturization trend, and also the power electronics increasing the power and voltage and things like that, everything goes against the climate reliability. So if you are increasing the voltage, and that goes against the climate reliability, and that way this problem will be much higher when we look into the electrification and related aspect. So everything what we look at is, one part of that one is to do with the humidity is forming such kind of condensed water layer on the board, and this condensed water layer is acting as a parasitic kind of a current conduction media. This is happening because of the corrosion process and electrochemical process what is happening on the board, and that goes into different failures. And most of these failures are transient effect, which means that when that kind of condition exists on the from the environment inside the device, and then you get a sudden failure. So it's not an aging failure, you get a sudden failure because of this effect. And many different types of failures you can get by this process, although I'm not going to the details. And it can be at the board level, or it can be at on a particular component, because all these board level or take the component, there are many materials on it. Yes, thank you. There are many materials on it, and coupling different materials, and that can cause when there is an environment, like it's not necessary to be humid.